Hello, welcome to Recitation Week 6 for the EE2423 Network Theorem. Today I will be solving some problems on Thevenin's and Norton's theorem. So basically, this is a technique that can be used to simplify any resistive linear circuits, and Thevenin's theorem says that for any linear electrical network containing only voltage sources, current sources, and resistances can be replaced at terminals AB by an equivalent combination of a voltage source, which is the Thevenin voltage, in series connection with Thevenin resistance. Okay, so it can be applied to any linear network containing voltage source, current source, both dependent or independent, and containing any resistors. Okay, so any linear circuit can be represented by Thevenin voltage source in series with Thevenin resistance. This is Thevenin circuit, and the dual is the Norton. Why is it dual? Because by using source transformation technique, you can convert from Thevenin into Norton, because Thevenin is using voltage source as a Thevenin voltage. Then in Norton, it is replaced by the Norton current source IN in parallel with Norton resistance, right? Okay, so if you can express the circuit using Thevenin circuit, then you can always express it or convert it into Norton circuit and vice versa. So they are interchangeable by source transformation. Okay, so let's start solving some problems. The first problem, we have voltage source 72 volt and resistor here 12 ohm, resistor there 5 ohm, here 8 ohm, connected to another resistor 20 ohm, and we have our terminal right here, AB. So the question, what is the equivalent Thevenin circuit for this particular circuit? Okay, so we can start by computing the Thevenin voltage first, or the Thevenin resistance first. So let's do the Thevenin resistance. Okay, okay, so we compute it by removing any independent source. Here we have a voltage source, so we can remove it by replacing it with the short circuit, right? Why short circuit? Because when we deactivate a voltage source, for example in this 72 volts, if we deactivate it, then it means that we turn it off, so we convert it into a 0 volt, right? 0 volt voltage source. So if you have a 0 volt voltage, it's just a short circuit, right? Because there's no potential difference in a short circuit, right? So that think that is the reasoning why we replace the voltage source with the source circuit. Okay, so this is the circuit that we have with 5 ohm, 8 ohm, and 20 ohm, 12 ohm. Okay, here is the same terminal, so we want to compute the resistance here, right? Okay, so let's simplify this. Okay, this looks complicated, so we can simplify it. So this is actually equivalent to this circuit right here, because let's keep the 12 ohm here, but let's move the 5 ohm. So 5 ohm is connected to the 12 and the 20 ohm, right? So say I can put it here, right? The 5 ohm, and this is 20 ohm, right? And 5 ohm and 20 ohm, they are connected together. Okay, and afterwards it is connected to the 8 ohm. Okay, I have 8 ohm here, it's connected to the 12 ohm resistor, so 8 ohm here. Okay, so these are the same circuit. Don't forget the terminal AB we have. So here's B, and A is between 8 and 12, so this is A. Okay, so we can simplify this, right? Let's do it here. So we have 12 ohm, 5 and 20 in parallel, so 5 parallel 20 is 5 times 20 over 5 plus 20, right? 100 over 25, which is 4 ohms. So we have 4 ohms, but this 4 ohm is in series with the 8, so we have another 12 ohm. Wonderful, because now we have 12 ohm resistor in parallel with 12 ohm, so the total resistance is just 6 ohm, right? You get half of the resistance. So this means that the Thevenin resistance is 6 ohm. Okay, how about the Thevenin voltage? Well, we should do our circuit analysis, so let me copy the problem again. Okay, so basically we want to compute what is the voltage in this AB terminal, right? So let's use a node voltage technique, because we can define here VA, VB, and this is VAB, so let's just call it the Thevenin voltage. But here we know that VA is, we put ground here, then VA is 72 volt, right? Okay, so we know VA is 72 volts, so let's just write our node voltage equation. So here, so let us define the current going out from this node and that node. So at node VB we have VB minus 72, right, over 5 plus VB over 20 plus VB minus V Thevenin over 8. equals 0. This is the first equation. The other equation is coming from this node A. So we have V Thevenin minus VB over 8, right? And then plus V Thevenin minus VA, which is 72 over 12 equals 0. Okay, so I have two equations, two variables. We can simplify it into this equation. So I have, you can work this out. I get 15 VB minus 5 V Thevenin equals 72 times 8, and this one is minus 3 VB plus 5 V Thevenin equals 72 times 8. Okay, great. You can add things up, right? The table voltage will cancel. We have 15 minus 3 is 12. VB is, sorry, this should be 2. So you have 10, 72. Okay, 7 to 0. So VB is what? VB is 720 divided by 12 is 60 volt. Okay, therefore the Thevenin voltage is, you can work things out to get the Thevenin voltage. I got 64 64.8 volt. Okay, so you can replace the circuit with the Thevenin circuit. So you have a voltage source 64.8 volts series with 6 ohm. So Thevenin voltage, Thevenin resistance. Okay, this is the equivalent circuit for this problem. So let's do the second problem. The second problem is asking for a Norton equivalent circuit. So this is the circuit. We have 15 amp current source. We have bunch of resistors, 8 ohm, 2 ohm, here 10 ohms, and 12 ohm. Cool. Another AB terminal, and it's asking for Norton equivalent circuit. Okay, we can do the same analysis by replacing the current source with an open circuit here to get the Norton equivalent resistance and work things out, right? So okay, so let's compute the Norton resistance. Okay, let's do it quickly. So this 15 amp current source becomes an open circuit, so we just have this circuit. So this series of resistance 2, 8 and 10, and they're in parallel with 12, right? So we have 2 plus 8 is 10 plus 10 is 20. So we have basically 20 ohm and 12 ohms. Sorry, this is ohm, and they're in parallel, right? So therefore the Norton resistance is 20 parallel 12, so 20 times 12 over 20 plus 12, right? So you have 4 times 5 times 4 times 3 over 20 plus 30 is 32. 32 is 2 times 4 times 4, right? So times 4, 8 times 4 is 32. Okay, so cancel, this 15 over 2 is 7.5 ohm. Okay, but there's another way. So this way we have to compute the Norton current source independently, right? So let's do another way. Let's use source transformation, right? So we transform this current source into voltage source. So by source transformation we can transform it into voltage source in series with the same resistor there, 8. Still have 2 and 10, and they are in parallel with 12 ohm, and here's the terminal AB. Okay, what's the value here? Value here is 15 times 8, right? So 120 volt. 120 volt. Okay, this is 8 ohm and 2 ohm. They are in series. We can replace them with 1. This 8 plus 2 is 10 ohm. Okay, now we have this, and this can be rearranged, right? So you can rearrange series like this, so you have 10 ohm, 10 ohm, right? They are the same. Okay, so since they're in parallel, we have a single resistor there, just 20 ohm. And let's do last transformation, current source with a 20 ohm. This is 12 ohm, then this is the AB terminal. What is this? Current source here is 120 divided by 20, right? So we have 6 amp, and we know that this is 7.5 ohm, right? So this is 7.5 ohm. Okay, so here we immediately get Norton equivalent circuit. So V Norton is, sorry, the current Norton is 6 amp, and this is the Norton equivalent circuit, 7.5 ohm. Okay, very simple. Let's solve the last problem. This is a little bit more interesting. So I have this circuit, 36 volt, with a flip sign on this voltage source, and this is more practical because the resistors are in kilo ohms, which is what we have in real world. We have kilo ohms. Usually we use kilo ohms resistors. 18 milliamps, 60 kilo ohms, 15 kilo ohms, And okay, that's it. Okay, so we have this circuit right here, and the question is as follows. Suppose that we have a voltmeter. So we have a voltmeter, and we want to I have a voltmeter volt, and this voltmeter will be connected to this AB terminal. But this voltmeter has 100k ohms internal resistance, and the question is, what is the reading of this voltmeter when we connect this voltmeter into terminal AB? So what is the voltage reading from this voltmeter? So that's the question. So essentially, I can copy this again. Okay, so basically we can, since we connect this voltmeter into terminal AB and it has 100k ohm internal resistance, then when we connect it, we put AB with this 100k ohm resistance, and the reading by this voltmeter is the same. So the voltage reading from the voltmeter is the same as the voltage across this 100k ohm resistor. So we want to find what is VAB here, right? They are equivalent. Okay, so to solve it, let's use a source transformation technique, right? So we have a voltage source in series with this resistance, so we can transform it into current source like this in parallel with this 12 ohms. So what do we have? We have, okay, since the sign is flipped, then we have to flip the direction of the current source to the other direction. We have the same 12k, the same current source which is 18, same resistor there, 60k, 15k, 100k, and VAB. Okay, what's this current? This current is 36 divided by 12k, so the current is 3 milliamps. Okay, but they are in parallel, so you can simplify it into 18 minus 3, so 15 milliamps, right? And these two resistors are in parallel, so 12 parallel 60, right, is 10. So you can compute that it's 10k actually, and series with 15k and 100k VAB. Okay, so let's do last transformation, right? If we convert it back into a voltage source plus minus with 10k, here we have 15k, the same 100k VAB. So what is this voltage source? The value here will be 15 times 10, right? So 15 milliamps multiplied by 10k ohms is 150 volt. Here 10 plus 15, I have 25, so 25k. All right, so I have 25k, so I have 150 volt and 100k ohm there. So we can use voltage division, right? So the VAB is nothing but 100 divided by 100 plus 25, so the total resistance multiplied by 150 volt, right? 100 over 125 multiplied by 150, this is 4 over 5 times 150 volt. This is 30, so 120 volt. Okay, therefore this voltmeter will read 120 volt across this AB terminal. Right, so that's the end of this recitation. If you have any question, please contact me, send me email, or come to my office hour as usual. All right, thank you, and I'll see you later. Goodbye.